Let's talk about theorems for type systems. A few days ago, we saw the simply typed lambda calculus, which came with a very powerful theorem, which says that all programs in it terminate. Obviously, a theorem of this power is only possible for a very restricted language, and we ourselves set about making our language more powerful than the theorem could accommodate. So given a general type system, what theorem might we want to have be true of it? Now first you should ask why we should even need a theorem. Well, it's because there are two very different systems operating here. The type checker statically looks at the program and never ever considers the program's execution in detail. The evaluator, such as the interpreter, for example, actually runs the program dynamically. As a result, these two programs are very different in character. One of them looks only at text, the other one looks at values. Therefore, the kinds of things they look at is very different. The type checker will usually look at branches an evaluator will never look at. An evaluator, in turn, will look at every term many times potentially, whereas the type checker might look at it only once. That's why it would be really nice to know that our type checker is actually telling us something useful about the program's evaluation. In other words, the key question is this. The type checker is making a static prediction about the program's behavior. Is the static prediction accurate? Now we usually care about a theorem that's called type soundness. Soundness says the following thing. If we have some program, E, and it has a type T, and when run, E is going to produce some value V. Now notice that we've already made a connection to both the static side where E has a type and the dynamic side where E is going to evaluate to a value. Then we would like it to be the case that V, the value produced by the program, also has type T. And if this is the case, then we can safely say that the static type checker was able to correctly predict what kind of value we were going to get out up to the granularity that the type system permits without ever running the program. Now, soundness is usually proven as a pair of lemmas. The first one says that if E has some type T and E takes a step of execution, then the new program is also going to have type T. This is called preservation, meaning that the type of the program is preserved during execution. The other one says that if E has type T, then either E is already a value, we're done, or there must exist some term that E can reduce to. In other words, if the program has a type, then the program will not get stuck. This is called progress. The final theorem about soundness comes about through a very elegant interleaving of progress and preservation steps. But before we get there, we need to understand that something tricky can happen. We haven't told the whole story about progress. Consider a term like division by zero, which in most programming languages that have static type systems doesn't yield a value, but also doesn't yield another step of evaluation. Rather, it reduces to some kind of known exception. We'll get back to this in a moment. So the way we prove soundness is by combining progress and preservation steps. First, we start with some program that has a type. The fact that it has a type tells us that it can take a step. That's what progress told us. Now, having taken a step, it must have the same type because that's what preservation tells us. In turn, it can take another step, which must be of the same type, and so on and so forth until we either get an answer, we never get an answer, but preservation will tell us that at every point we had the same type anyway, or we get one of these well-known exceptions. Now, this business about exceptions might be a little troubling because it sounds a little bit like a cop-out for the type system. Actually, it's not. And to put this in perspective, let's go back to a well-known paper from the early 1980s, which is a seminal paper about type inference for Smalltalk. In the abstract of the paper, the authors say, Smalltalk is a type-safe language in the sense that when you encounter an object of the inappropriate class, it will only result in a runtime error of the form message not understood. But it would be advantageous for the programmer to be informed of this error at compile time rather than during program execution. So right there, we have an exception that would have been only raised dynamically that the type checker is now informing you about statically, which means it can never occur at runtime. So that's the critical thing that the type soundness result gives us. Yes, we might still get an exception, but we now have a guarantee about a whole bunch of exceptions that can't occur. And in fact, there may be many more that you simply never considered, but the type checker guarantees that you never need to think about them at all. If you can deal with the kinds of exceptions that the type checker permits, all other exceptions will never arise. So to summarize, this is what a type soundness theorem tells us. If E has some type T, then either it's going to produce a value, in which case we know what type the value is going to be, it's going to be T, or E doesn't terminate, but preservation will tell us that we have something that's computing of the same type all along, or E reduces to some known exception, and the exceptions that are not listed in this set we don't need to worry about. That's a very powerful guarantee indeed, and that's why we'd like to insist that when we work with a type system, we only work with sound type systems.